All right, just a few more topics on logarithms. Some properties of logarithms are that if we have log base a of 1, it's going to equal 0 because when we flip it into exponential form, we're going to end up with an exponent of 0, and anything with an exponent of 0 equals 1. When you have a log with a base a to the exact same of a, it's going to equal 1 because when you convert it, you get anything to the power of 1 equals itself. When you have log base a of a to the x power, you kind of have an exponent raised to an exponent. You can change it and have it, because they're inverses. So this one is a double part. And we have a with the log of a to the x. These are both going to equal x. So again, if you kind of think about it like this part cancels out, or this part cancels out, all I'm left with is x. They're inverse properties. They're inverse operations. And if log base a of x equals log base a of y, well then, of course, you know x equals y, because they are the same exact things. We also have this idea called a natural function. And this is when we use that, the topic of e, okay? And we've kind of talked about that already. So the f of x equals e to the x power is 1 to 1, so it has an inverse function. So the inverse of e to the x is called the natural log, okay? So this would be ln. So this is called a natural log. And so if we sketch it out real quick, if we had the graph of e to the x, it would look something like this. Okay, where we have a y-intercept of 0, 1. We could say that this is -1, 1 over e. And then this could be x is 1, y is e. Whereas our inverse function, so again, this is the graph of e to the x. We can use Desmos as well. Our natural log is going to look like this. So again, I'm flipping my x and y values. This is not correct because we have an asymptote right here. Let me redraw that. So if we use Desmos again, okay, here is my graph of e to the x power. All right, let's find. So maybe we go e. So you can see e is approximately 2.7. E to the x power looks something like that. If we graph the natural log, of x, again, they're inverses. And then if we graph the line y equals x, you can see the asymptote right there. So just another way to look at it. Inverse functions. Some properties of e, okay? properties of natural logs, excuse me. Properties of natural logs. ln of 1 equals 0 because e to the 0, again, if you switch its form, is going to equal 1. ln of e equals 1 because e to the first equals e. I like to think about it as ln, natural log and e's kind of cancel out because they are inverses. So again, if I have ln of e to the x, it's just going to equal x because these are going to cancel out, and kind of it's very similar. So and if I have e to the ln x, again, these are going to cancel out, so it's just going to equal x. And lastly, again, they're very similar to the properties of logs that we talked about already. If ln x equals ln y, then x equals y. So that was real quick, some examples about natural logs. Now to kind of talk about the properties, and we're going to use some kind of change of base formulas. So real quick, I want you to make sure you have this in your notes. Okay, so again, how do we change bases? So we'll do an example here. We're going to say that we have log base 4 of 25. And again, we like keeping it in base 10. Base 10 is easier for us to use. So what we're going to do is we're going to take log base 10 of 25 and put it in our numerator. And then we're going to put log base 10 of 4 in our denominator. And this, you could actually use your calculator to solve. So again, if I were to go to Desmos, or if I wanted to use this other calculator, I could again say, all right, I've got my log. This log is naturally in base 10. So it's kind of always in base 10. So I would say log of 25, close my parentheses, divided by log of 4, close my parentheses, and I get approximately 2.3219. So this is approximately 2.3219. One more example, very similar. Okay, again, I don't have a base 10. That was the problem. So in this example, I have a base of 2. It's hard for us to calculate that. We like having base 10. So I'm going to take this 12 and put it in my numerator. And I'm going to take that 2 and put it in my denominator. And then I can use my calculator just like I did last time. Okay, I can take my function. I can say, okay, let's go log. This is in base 10 because it's the standard. 12 divided by, divided by log base 2. And I'm going to get 3.58. We can call that 3.5850. So again, this approximately equals 3.5850. It's super similar with natural logs. Like we just got done talking about natural logs. So say I have I want to use natural logs, so we can use these same examples. I could say, hey, I want log of, we'll go back to our first example, base 4 of 25. I can use the inverse, which is the natural log. I can say ln of 25 over ln of 4, and it's going to equal the same thing that we got up here, 2.3219. So again, that might be easier for you when you're typing into your calculators if you're just using natural logs, you might say, okay, 25 divided by natural log of 4. Again, I got the same exact answer. So you can change the bases using the natural logs as well. Some other properties, and again, I'm going to take a picture of these because these are super important that you have written down. Oh, that was not clear. So if we look at this first example, okay, basically what I'm doing is I'm saying, hey, I've got some numbers inside of my parentheses, and instead of, keeping them together like that, I could split them up like this. And it works, as you can see, it works the same way with natural logs. Okay, so again, we can manipulate our equations to potentially get something that maybe is more useful for us. So if I were to say, all right, I want you to take the natural log of 6 and write it in terms of the natural log of 2 and the natural log of 3. So we would say, okay, well, the natural log of 6 is the same thing as the natural log of 2 plus the natural log of 3. And that would be my answer. Again, if I had division, say I had the natural log of 2 over 27, I would just say, all right, that's like saying the natural log of 2 minus the natural log of 27. Now, again, 27 is not in base 3, so I could rewrite this as, well, the natural log of 27 can really be the same thing as 3 to the 3rd power. Now, if you look at property 3, okay, it says, hey, if I have a log or if I have an exponent and I have an additional exponent, so like right here and right here, what I want to do is I want to bring that number out front. So I would rewrite this as the natural log of 2 minus 3 natural log 3. So that is something you're going to want to get in the habit of doing, is moving that number out front. Okay, let's maybe do one more example of condensing logarithmic expressions. So let's say that we have 1/2 log 10, log base 10 of x plus 3 log 10 x plus 1. What I would first want to do is I would say, okay, I think I could, again, use this property. I can take what's out front and move it right here. I can take what's out front and move it over here. So I'm going to say this is log base 10 of x to the 1/2 plus log base 10 of x plus 1 to the 3rd power. And then again, because I know that it's adding, that's like the first property up here that says I can combine them and multiply them. So because they have the same base, they're both base 10, I can combine them. So I would say this is actually like log base 10. X to the 1/2 power is the same thing as the square root of x. And then this is x plus 1 to the 3rd. So you can go both ways. You can expand it or you can contract it. And I will ask you to do both of those.